Single degree of freedom vibrations today could be a beam forced in some way such that one mode dominates and we are using a single mode approximation, could be our usual spring mass system with a damper, block and a force, could be a torsional vibration of a shaft with a disc. It doesn't matter. We are interested in a situation where the governing equation looks like this. So there is a mass or an inertia, there is x double dot, Cx dot represents some viscous damping, Kx a restoring force and some f of t. We will look at this system or this equation in the frequency domain. The reason why we can do this is that for one thing, if f of t is periodic, then we can write it in a Fourier series, and if f of t is not periodic, if it is aperiodic, we can still write it using a Fourier transform in the frequency domain. And then because this underlying equation is linear, we can add up the responses for the different frequencies to get the net response. We are able to do this because the system is linear, and linear systems are studied fruitfully in the frequency domain, hence the frequency domain. So here's the equation now. In the frequency domain, we think of some forcing f0 bar sine omega t. Omega is an arbitrary frequency. We will keep changing this and see how the system behaves. The bar is for an analytical simplification, which you will see now. When we divide by m, what that c becomes is c by m, but we write it as 2 zeta omega n, where omega n squared is k by m. So this omega n is called the natural frequency of the system, this zeta is called the damping ratio of the system, and now I have dropped the bar over here. This f0 is f0 bar by m. The solution for this system has a complementary solution and a particular solution. The complementary solution is found by looking at the characteristic equation. Looking at this equation, we write the characteristic equation from here, r squared from here, 2 zeta omega n r, r for this one derivative, omega n squared from here equals 0. This is the characteristic equation. The solution for this quadratic equation is simple. It is r is minus zeta omega n. From here, the 2 is gone because eventually it will be divided by 2. So it's minus zeta omega n, and similarly there has been a 4 removed from inside the square root, and we have zeta squared minus 1 with brackets and then omega n squared. If zeta is bigger than 1, both solutions are real and negative. You can think that through. What you will see here is zeta is more than 1. This quantity is less than zeta squared omega squared, so its square root is less than zeta omega. Even when you add it, something negative remains, and when you subtract it, of course it is negative. This is the overdamped case, zeta greater than 1. Zeta equals 1 is the critically damped case, and zeta less than 1 is the underdamped case, which gives oscillatory solutions, and usually we are most interested in this case in a vibrations class. For zeta less than 1, the roots are then written as minus zeta omega n directly from here, and this part, because zeta is less than 1, it gives an imaginary part over here because of the square root. This we write as plus minus I omega d. Omega d is sometimes called the damped frequency or the damped natural frequency, if you like. This is omega n times the square root of 1 minus zeta squared, and you will notice that if zeta is small, say less than 0.1 or so, it is really not very different from omega n at all. So if zeta is 0.1, zeta squared is 0.01, this thing is approximately 0.995. So the complementary solution is e to the power minus zeta omega n t from the real part, and from the plus minus I omega d, we have a sine omega dt plus b cos omega dt. This a and b are arbitrary constants. They will be fitted based on initial conditions. If zeta is greater than 0, eventually this complementary solution decays to 0. At that point, the role of the initial conditions is gone and only a steady state solution remains. The particular solution, it is better to use complex variables. The particular solution is also the steady state solution, as you will see, the particular solution we find. So over here, we are writing it again. Here is the governing equation, but we are now using complex variables. The f0 sine omega t is written as f0 e to the power I omega t. The reason we do this and the reason we can do this is that in this equation, which is strictly linear with real coefficients, what happens is that the real part of this gives one solution, the imaginary part of this gives another solution, those two solutions remain separate. And so if we solve it for this input and take the imaginary part later, we get the solution for F0 sine omega t. For the complex forcing, we will assume a solution of the form x0 e to the power I omega t. This x0 is a complex number which remains to be found. When we substitute this into the governing equation here, we get this equation, minus omega squared x naught here for the second derivative of this quantity. There was a dot here, apologies. There's a dot here. So this dot leads to I omega over here, and then over here omega n squared x0 is f naught. We are able to solve this easily. X0 comes out, this again because it is linear, so f0 divided by this quantity in the denominator. Now what we will do is we will make the denominator real, and I'm going to use a trick that is in this box over here. It's a very routine trick. 1 over p plus iq is written as p minus iq by p squared plus q squared. This upper part has a magnitude of square root of p squared plus q squared. When I cancel it, then I can write it as 1 over. So this quantity here is the same as 1 over p squared plus q squared inside a square root times e to the I psi, where psi is some phase. That phase is actually tan inverse q over p. So this quantity here, 1 over p plus iq, is this magnitude, and this unit modulus complex number, the phase of which is this. When I do the same trick here, this part comes over here like this, the real part gets squared, the imaginary part gets squared, they get added and put inside a square root, and it has to be multiplied by e to the I psi. E to the I psi, that psi is minus tan inverse, I'm just following this formula here, 2 zeta omega omega n in the numerator and omega n squared minus omega squared in the denominator. Additionally, this part here is now real, and I am going to call it an amplitude A for simpler writing. So this x is x0 e to the I omega t, is a e to the power I psi times e to the I omega t, is a times e to the I omega t plus psi. I take the imaginary part of that, I get a sine omega t plus psi. So you can see I found the amplitude of the solution here, and I found the phase of the solution. This phase is negative or positive, whatever it may be. This is how the solution is shifted. It is a sinusoidal solution, but it is shifted in time from the forcing. Let's look at the phase first. For zeta small, that means light damping, and low omega, when we look here, the numerator is positive, but this is small. Omega is low, so the denominator is just some number, it's not very small. What happens is tan inverse of a small number is just some small angle with a negative here. And so what happens is there is a small phase lag, and the response is almost in phase with the forcing. When omega approaches omega n from below, omega n minus, then what happens is that the numerator is no longer small. It is now to be treated as some finite number. This quantity goes to plus infinity. The tan inverse of that is pi by 2 with a negative. And so what happens is that the phase lag approaches pi by 2 or 90 degrees when omega approaches the resonant frequency. When omega crosses the resonant frequency, then it becomes minus infinity. The tan inverse is minus pi by 2. Then with a minus, it seems like the phase is plus pi by 2, but remember that the tangent is pi periodic. So we are taking the tan inverse, the correct phase is actually still minus pi by 2. And you can see that even better when you think of this omega as much bigger than omega n squared, omega squared much bigger than omega n squared. Then what happens is this quantity becomes negative in the denominator but small overall. So the tan inverse is a small negative number, and with the negative it becomes a small positive number. But you subtract pi from it because the tan inverse allows that, and then the actual phase lag is slightly below pi. So what happens is that when you can work it out with greater care, you will get the same result. What happens is that for small forcing frequency, it is almost in phase with a small phase lag. At resonance where omega is equal to omega n, it is exactly pi by 2 out of phase and lagging with pi by 2. And then for much higher frequencies, it is almost exactly out of phase, lagging by a phase that is almost pi. So here's the expression for the amplitude again. And for small zeta, for small damping, this term is small. So away from omega equals omega n, where this term would also be small, away from that point where this is big, it is clear that the amplitude is f0 by the magnitude of omega n square minus omega square. At omega equals omega n, the amplitude, this one goes to 0, so then the amplitude is like this. This omega becomes omega n and you take a square root. It is like this. This is very interesting and important. This means that at resonance, basically the amplitude is determined by the forcing amplitude. I should have written f0. By the forcing amplitude, and it is inversely proportional to the damping ratio. So for example, if you have a motorcycle and you can double the damping ratio, then the vibrations you will encounter as you pass through structural resonances will have exactly half the amplitude. They will be down 6 dB. It will make the motorcycle seem much better. These large amplitudes occurring near omega equals omega n, this is the simplest type of resonance. You are familiar with it. I'll point out something, that this omega n square minus omega square over here, the whole thing squared is quadratic in omega square, if you think of omega square as a variable. But this part is linear in omega square, so the true maximum amplitude occurs where this is least. If you shift it a little bit left, it takes an even smaller value, okay? And so the actual magnitude maximum occurs at a frequency slightly below omega n. You can find it by saying this denominator needs to be minimum, so you take the reciprocal, then it needs to be maximum, you square it, it still needs to be maximum. If you let this z be omega square, or then this thing inside the square root has this form. You can differentiate with respect to z, set it equal to 0, you get 2 times a minus z is equal to b, you solve it, so you get z. The shift from a is proportional to b, b has zeta squared in it. So there again you can see that it shifts a little as the damping ratio increases. The graph of the amplitude versus forcing has this special point omega n. For very small frequency, for very small omega, this term is 0, that is 0, so it is just f0 by omega square, another square and a square root. So f0 by omega n square, remember that f0 is actually f0 bar by m. So this is the static response. Whatever is the spring, the damping is not important, the mass is not important. If you load it very, very slowly, you will just get a static response, static deflection of the spring. For very large amplitude, over here you can see this omega squared and squared dominates everything else, and so it is f0 by omega squared, not omega n squared. And then if you remember that f0 by omega squared is just f0 bar by m omega squared, this is the inertial resistance. At very high frequencies, the inertia dominates. If you look at this governing equation, you will see that at high frequencies, this term is bigger than anything else. At low frequencies, this term is bigger than anything else. There is a special frequency, the natural frequency, where this term exactly cancels this term, and this one is counteracted by this. So x dot is in phase with f, which means that there is a 90-degree phase difference between f and x. Over here, low frequency, x balances this, so it is in phase. High frequency, x double dot balances this, so the acceleration is in phase, which means the displacement is 180 degrees out of phase. So that tells you this part of the curve and this part of the curve, which is mostly unaffected by zeta, the damping ratio. And then over here, depending on what zeta is, this will turn around and have a peak over there. The peak will shift slowly to the left. As the resonant amplitude goes down, you will get a family of curves with increasing zeta. The phase psi, I am plotting the negative of it and calling it the phase lag. It will start at 0 frequency, stay close to 0 for a range of frequencies. Close to resonance, it will start increasing. At resonance, it will be or very close, where it is equal to the natural frequency. Over there it will be pi by 2 at resonance, and then it will level off at approaching pi. And then if the damping ratio increases, this transition will occur over a larger region, larger range of frequencies, and if the damping ratio is very small, then it will occur over a very small range of frequencies. Now let's consider base excitation. The cartoon is a mass supported by a spring and a dashpot which is on a base which is moved by some external agent. You can use models like this to study, for example, the response of a vehicle which is driving on a road which has undulations in it, and there are other applications. The equation of motion based on a free body diagram like this is mx double dot is, here's the spring force which depends on both the travel of the mass as well as the travel of the base, and the dashpot force, which you move the x terms over to the left side. This is the equation. We will again look at it in the frequency domain using a sinusoidal base excitation. We will use complex variables again, and so we will assume that u0 sine omega t will be replaced by u0 e to the I omega t, and this coefficient will appear over here because of these two terms. We will assume x is equal to x0 times e to the I omega t, and so that x0 is like this, the x0 is this complex part. And then we will look at the amplitude of that, which will look like this. It's called the transmissibility and a phase. The amplitude now has two parts. For the numerator part, we will just take the magnitude, so it is k square plus omega square c square. For the denominator part, we will do the same multiplication above and below that we saw earlier, and so once again we will get this magnitude, but the phase will have two contributions. The numerator phase will be directly taken, the denominator phase will be subtracted. The numerator phase is tan inverse omega c by k from imaginary by real. The denominator is tan inverse omega c by k minus omega squared subtracted. Now, one thing I want you to notice is that for small omega, what happens is this denominator is smaller than this denominator, and so this number is bigger than this number, and so there is a negative net phase, and so there is a small phase lag. However, if omega is small, the phase lag is small, just negative. For omega close to omega n, what happens as omega approaches the natural frequency, this quantity goes to infinity, this tan inverse of that goes to pi by 2, this is just some number. And so what happens is the phase is not near pi by 2. However, if the damping is very small, then it is. For very large omega, what happens is this one gets close to pi by 2, this one gets very small, and so in fact there is a pi by 2, the phase is pi by 2. Why is it so? You have to look here and see. For very large frequency, you know that the mass does not move much anyway, but over here between this one and this one, the force from the damper becomes much bigger than the force from the spring because of the large frequency. And so when you apply a displacement u, in fact a u dot is the force acting over here. So there is a 90-degree phase difference between the displacement input and the force actually acting, and then between that force and this mass there is a 180-degree phase difference. That 180 and 90 combine to give you a 90-degree phase difference. A final point is that when omega square times m is equal to 2k, so you come over here, you see this c square omega square, they are the same, these two are the same. Over here you have k square. If m omega square is 2 times k, then this term equals that term, and what happens is the transmissibility is 1 regardless of the damping ratio. This is a peculiar feature of base excitation with linear viscous damping. Let's think about behavior near resonance. So first let's not have the damping term, and let's think of the forcing as being at resonance, omega n, or we'll think of it in complex term. We'll try a solution x0 e to the I omega nt. When we substitute this into the left hand side, it cancels, so that solution fails. We can try a solution x0 times t e to the I omega nt, then x dot can be found. It is like this, x double dot is like this. Here this one is the derivative of that one, and then the derivative of this one, you drop the t, that's this one, and the other one, this one comes in here, that's this term here. When we substitute x double dot plus x is equal to f0 e to the I omega t over here, this one here, in this equation, what happens is this term here cancels with this term here, but this one survives. And so we have x0 is equal to f0 by I 2 omega n. You can move the I to the numerator. And then the actual solution x becomes f0 by 2 omega n with a minus I here, t e to the I omega t. Remember that this is cos omega t minus plus I sin omega t, but I am multiplying by I and I want the imaginary part, so the minus cosine comes out. And so the solution is minus f0 by 2 omega n t cos omega n t. This t over here shows that the amplitude grows linearly with time. This has several implications, and one implication is that if you have large resonant amplitudes, they are not established instantly, so they take some time to build up. For example, if your amplitude versus frequency curve is like this, if you are spinning up a rotor and you have to pass through a resonance in the frame, if you increase the speed quickly, what will happen is you will not reach this amplitude and then go back. You will sort of hop over quickly over here because you will not reach the steady state at resonance. It takes time to build up. While I have this figure here, I just want to show one more thing behavior near resonance, which is that suppose due to some non-ideal behavior, there is a small nonlinearity in the spring or in the restoring forces, let us say epsilon times x cube. So what happens is, far away from resonance where the amplitudes are not big, it is just like the linear oscillator. So this part of the curve and this part of the curve don't change, but where you reach resonance, the amplitude is big. There this one becomes a bit important, and it is like the spring restoring force is x plus epsilon x cube, and it is like a stiffer spring. It is as if this has a higher coefficient. The derivative of this is 1 plus 3 epsilon x square. I have missed a term here. It doesn't, I should add this term here. Apologies. So because the spring becomes stiffer at large amplitudes, it is as if this peak wants to move to the right when it is high, but not move to the right when it is not high. And the result is that this resonant curve can actually bend like this. You can have a frequency range where you have multiple solutions. Over here, 3 are possible. In fact, such solutions occur, but this one is unstable. 2 different amplitudes are possible for a nonlinear oscillator at steady state, both of them stable for the same forcing frequency for the same amplitude. In fact, what happens here is that if you start at a low frequency, then you get a certain amplitude, you slowly increase the frequency, you follow this curve. Over here, solution disappears and you jump down here, and then you go like this. When you lower the frequency, you may come like this, you come to this point and then jump up and go like this. In this intermediate region where both solutions are possible, suppose you are on this solution, if you smack the system and give it a different initial condition, after transients die, you may come back here or you may settle down here. Both of those solutions are stable. This you will not see in practice. If we think of slowly changing amplitudes for near resonant behavior, then some work energy based insights are available. Why would amplitudes be slowly changing? One way would be that the forcing itself is small. Another would be that the amplitude has become large and then in relative terms the forcing is small. In either case, slowly changing, the way we think of it is we think of the amplitude as some A. The solution near resonance is A sin omega t with a pi by 2 phase lag, so minus A cos omega n t, omega n being the natural frequency, and here A is slowly changing. This is an approximate sort of analysis. The energy input rate or power input rate due to the forcing is f of t times x dot dt integrated over one oscillation. This is the power input rate on a per cycle basis. You will notice that I am mixing some units here because so far I had f0 bar, then f0, so in some places it was divided by m and in some places not. I'll try to take care of it by introducing some fitting constants, but you can do the same thing more carefully and you'll get exactly the same result. But I'm just warning you that the units may sometimes seem a bit funny. Here is the force f0 sin omega t, here is x dot, the derivative of this thing here with an A dot cosine and an omega A sine. The A dot slowly varying means this is very small compared to this, so the main game is here. Also, if you think of A dot as a constant, you will see sine omega t, cos omega t, the integral is 0 anyway. That's resonant forcing, omega n. Okay. So this part we will neglect. We come here. The sine squared has an average value of half. The coefficient f0 omega n a is here, and the average value of half is over the period of one oscillation, which is 2 pi over omega n. And I'm just going to note that this is equal to some constant alpha times f0 the forcing amplitude times a the response amplitude. This is the energy input per cycle due to the forcing. Suppose there is dry friction. For example, we are looking at an oscillator like this. So there's x double dot, mu is some effective friction coefficient. Signum of x dot shows that the force has constant magnitude. When x dot is positive, then it is one way with constant magnitude independent of velocity. When x dot is negative, it is the other way with constant magnitude independent of velocity. And then this is the spring term and this is the forcing. Suppose there is a solution, system like this. This is a friction force. The dissipation per cycle due to this friction force times 2 times the amplitude. So 2 mu a. Okay. Suppose there is a viscous damper, then the damping force is Cx dot. I'm not writing it out because you are familiar with it. The dissipation per cycle is the integral over one oscillation of Cx dot. That's the damping force times x dot. So Cx dot squared dt. This will give you the, the x dot is a sine omega nt. So the sine and the sine are obviously in phase, and it will give you an integral which is some constant times the damping coefficient C times a squared. The energy in the oscillation is, some stiffness times the amplitude squared times half. So E dot is K A dot. And now you have energy balance. The rate of change of energy is equal to the energy input minus the dissipation due to Coulomb friction minus the dissipation due to viscous friction. So we have E dot is K A dot is the input from here alpha f0 a, the dissipation due to dry friction and the dissipation due to the viscous damper. This gives us an equation of this type. A dot is some constant proportional to the forcing amplitude minus another constant proportional to the dry friction coefficient minus this term linear in the amplitude due to the viscous damper. Suppose there is no dry friction, this is easier. You know the answer, in fact, and what you will see over here, suppose this mu bar is not 0, is you see that there is a steady amplitude. The particular solution A equals constant is there, and then in fact there is an exponential approach to that amplitude over here because of this minus beta bar C and this A dot. The characteristic equation is R equals minus beta bar C. Okay. Now, when there is dry friction, and in the absence of the viscous dissipation, it is a little more interesting. You see, if the forcing amplitude is bigger than some critical number for a given frequency, the forcing amplitude, for a given friction coefficient, the forcing amplitude has to be somewhat bigger, and then the amplitude just increases and increases without bound. Dry friction in itself is not able to limit the resonant amplitude. Viscous friction is. Over here what happens is this A keeps increasing and eventually this dominates no matter how small the viscous friction. That advantage is not had by the Coulomb friction. So if you have dry or Coulomb friction, if the forcing amplitude is sufficiently big, you have unbounded amplitude, but the amplitude increases linearly. And if the friction coefficient is too big and the forcing is not sufficiently big, then what happens is that you have decay in amplitude which is linear. And in particular, if the forcing is also 0 and the viscous damping is also not there, then you find that the amplitude decreases linearly. So this is how two types of dissipation affect the amplitude, and you can get this insight by thinking of slowly changing amplitudes and writing an equation for the slowly evolving amplitude.